Ever catch a glint of rainbow in? Like a CD or maybe the edge of a glass?
Oh, yeah, those little flashes of color.
It's like the everyday light around us is holding a secret, you know?
Hmm.
A hidden spectrum just waiting to pop out.
Definitely.
Okay, let's unpack this because that fleeting glimpse of color is, well, it's our launch pad for today's deep dive.
Sounds good. Where are we headed?
We're plunging into the fascinating world of light. We'll be using the humble triangular prism as our guide,
Uh-huh.
and then stretching out to the vastness of the electromagnetic spectrum.
Right, the bigger picture.
Exactly. You've shared some brilliant material with us, and our mission today is really to unearth the most compelling and, frankly, sometimes mind-bending truths about how light behaves.
I mean, like where the colors we see actually come from?
Precisely. And how that visible light fits into the whole cosmic picture. We're going to explore how seemingly pure white light throws, well, a technicolor tantrum when it meets a prism.
Ah, I like that. A tantrum.
Yeah. Why those colors take different paths. And then, like I said, zoom out to see the full family portrait of light, the electromagnetic spectrum, and where our familiar rainbow fits in.
It's amazing, really, how a simple piece of shaped glass can unravel such fundamental stuff about reality.
Totally. So where do we start? With the prism itself.
Let's start there. Let's focus on what happens when light of just a single color, say pure red light, hits a triangular prism.
Okay. One color. Red.
As that beam goes from air into the denser glass, it bends. We call this deviation.
It deviates, right, towards the thicker part.
Towards the base, the thicker part, exactly. That's the first bend at the first surface. Then, as it leaves the prism on the other side, going back into air,
It bends again.
it bends again, yeah, this time away from the base. So it's like a two-stage change in direction.
Two bends. Got it.
Mm.
But it's not just random, is it?
Mm.
What decides how much it bends? The angle.
Good question. That total angle of deviation, the overall change in path, it hinges on three main things. First, the angle the light hits that first surface, the angle of incidence.
Makes sense.
Second, the prism's own shape, its geometry, particularly the angle at the top.
Right, the prism angle?
And third, the material of the prism, usually glass, and specifically its refractive index.
Ah, the refractive index.
Ah,
The refractive index, that's about how much the light slows down, isn't it?
essentially, yes. But here's the really interesting part. This refractive index, it isn't fixed. It actually changes depending on the color of the light.
Wait, really?
Yeah, or more precisely, the wavelength of the light. It's like the glass reacts slightly differently to each color that passes through.
So blue light and red light experience the prism glass differently. Why? What's happening there?
Fundamentally, it comes down to the speed of light. Now, all colors zip through a vacuum at the same incredible speed, right? And pretty much the same in air.
The speed of light, C.
But when they enter a different medium, like glass, they slow down. And the key thing is, they don't all slow down by the same amount.
Okay. It depends on the color.
It depends on their wavelength, which corresponds to color. Specifically, the speed of light in a transparent material like glass decreases as its wavelength gets shorter.
Shorter wavelength means slower speed in glass.
Okay, think of it like runners hitting a patch of mud. Some might get more bogged down than others.
Okay, I get that. So violet light has a shorter wavelength than red light. Does that mean violet gets more bogged down in the glass mud?
Exactly that. And since the refractive index is basically a measure of how much light slows down.
Higher refractive index means it slows down more.
Right. So violet light, because it slows down more, experiences a higher refractive index in the glass compared to red light.
Okay, higher refractive index means more bending, a sharper turn. So violet light, shorter wavelength, slows down more, higher refractive index, bends the most.
You nailed it.
And red light is the opposite. Longer wavelength, less slowing down, lower refractive index, bends the least.
Precisely. The deviation caused by the prism increases as the wavelength of light decreases. It's an inverse relationship.
Right.
So for visible light going through glass, violet light, that's around 400 nanometers or 4,000 angstroms, super tiny.
Yeah.
That gets deviated the most. And red light, around 800 nanometers, is deviated the least. It's all because of that difference in speed inside the glass.
Violet sort of tiptoes through slowly, red breezes through a bit faster.
That's a good way to put it, leading to those different angles of refraction.
Okay, that makes sense for single colors. But what about white light, like sunlight?
Yeah.
To our eyes, it just looks white. What happens when that goes through a prism?
Oh, the million-dollar question. White light isn't really a single thing. It's actually a composite, a mixture
A mixture of what?
of light waves with different wavelengths and therefore different colors, all the colors of the rainbow, basically.
You mean violet, indigo, blue, green, yellow, orange, red?
VIBGYOR.
Those are the main ones, yes.
Yeah.
And each of those corresponds to a specific range of wavelengths. Wavelength is really the defining characteristic of a color.
And we have the rough ranges, right? Violet's down at the short end, maybe 400 nanometers or so. Around 400 to 446 nanometers.
Yeah, and red is way up at the other end, like 620 to 800 nanometers.
That's the range. And you'll notice, as the wavelength gets longer going from violet to red, the frequency of the light waves actually decreases.
Ah, right. Frequency and wavelength are inversely proportional. Speed of light equals frequency times wavelength.
Correct. So now imagine this cocktail of wavelengths, this white light hitting the prism.
Okay.
Each component color inside that white light behaves according to its own wavelength. It hits the glass, slows down by a specific amount based on its wavelength.
And therefore bends by a specific amount. Violet bends most, red bends least.
Exactly. And this is where we get the beautiful phenomenon called dispersion.
Dispersion. The splitting up of the colors.
Precisely. Think back to Isaac Newton's famous experiment. Dark room, small hole letting in sunlight, prism in the path.
And boom, a rainbow on the wall.
A band of colors, the spectrum, not just a spot of white light, but VIBGYOR all spread out. Violet nearest the base, red furthest up.
It's incredible. He basically showed that white light isn't pure. It's a blend. Polychromatic, many-colored.
That was his conclusion. And while we draw it as neat bands, in reality, the colors blend smoothly, right? No sharp lines.
Yeah, it's more of a continuous gradient.
The key takeaway is the prism isn't making the colors. It's just acting like a sorter.
A very effective sorter, based on wavelength.
Right. It separates the colors already present in the white light. That splitting is dispersion, and the band of colors you see is the spectrum.
And the cause, fundamentally, is that change in the speed of light with wavelength inside the prism material.
That's the root cause.
So just to be clear, the white light hits the first surface.
Uh-huh.
And immediately the different colors start to separate because they bend by different amounts as they enter the glass. Violet takes the sharpest turn down, red the shallowest.
Correct. That's where the dispersion really kicks off.
Then they travel through the glass, getting further apart.
Mm-hmm.
And when they hit the second surface to exit back into the air, they bend again, separating even more.
Exactly. They refract again, bending away from the normal, and again, violet bends more than red, increasing the separation.
So dispersion happens mainly at the first surface, but the deviation, the overall bending, happens at both.
You got it. The prism reveals, it doesn't create.
We had some neat examples in the sources too. Like if you mix blue, red, and green light and shine it through a prism, you see them split.
Right, they'd separate out.
But if you shine that same mix through just a flat, parallel-sided piece of glass, like a window pane.
Ah, the glass slab example.
Yeah, they separate a tiny bit going in, but then the second surface is parallel to the first, so they recombine, and what comes out is pretty much white light again, just shifted sideways.
That's a great illustration. The non-parallel sides of the prism are crucial for the dispersion to become obvious. The slab cancels out the effect.
And there was another one with red, blue, and yellow light hitting a right-angled prism.
Yes, an isosceles right-angled prism. That one brings in another concept. Total internal reflection.
Oh, right, where the light gets trapped inside.
Potentially. It depends on the angle the light hits the inside surface and something called the critical angle for that specific color in that glass.
The critical angle, the point of no return.
Sort of. If the light hits the internal surface at an angle greater than the critical angle, it can't escape. It reflects back inside. If it hits at an angle less than the critical angle, it refracts out.
And the critical angle depends on the color, too.
It does, because it depends on the refractive index, which we know varies with color. Typically, blue light has a smaller critical angle than red light in glass.
So in that example, maybe the blue light hits the surface at an angle greater than its critical angle and reflects internally, while the red light hits at an angle less than its critical angle and escapes.
That's entirely possible, depending on the specific angles in the glass. The yellow light might even hit at its critical angle and skim along the surface. It shows how complex the interaction can be.
Wow. And quickly, the equilateral prism one.
Yeah.
White light hits face on, goes straight in, hits the next face at 60 degrees.
Right. And if 60 degrees is greater than the critical angle for all the colors...
Then they all undergo total internal reflection, bounce off that surface.
Exactly. It really highlights the interplay between the light's properties, the prism's geometry, and the material's characteristics.
Okay, and just to ground this with numbers again, you mentioned the relationship 11.5 yield lambda.
Right.
Speed of light equals frequency times wavelength.
Mm.
So for violet light, high frequency, like $7.5 times 1014 hertz, that gives the short wavelength 400 nanometers.
Correct.
And for red light, longer wavelength, 800 nanometers, that corresponds to a lower frequency, around $3.75 times 1014 hertz.
Exactly. They're inversely related, always linked by the speed of light in a vacuum, see?
Okay, so the prism does a fantastic job dissecting visible light. But as you said, that rainbow we see is just a tiny, tiny fraction of something much bigger.
Oh, absolutely. The electromagnetic spectrum.
Let's pull back and look at that bigger picture. What else is out there beyond the red and the violet that our eyes just don't pick up?
It's pretty mind-blowing. Visible light is just this narrow little window beyond the red end as wavelengths get longer.
Longer than red.
You first hit infrared radiation, think heat radiation.
Okay, like from a fire or night vision goggles?
Exactly. Then longer still, you get microwave.
Like in the oven? And for phones?
Yep. And keep going to even longer wavelengths, and you arrive at radio waves, TV signals, actual radio broadcasts. Huge wavelengths, relatively speaking.
Wow. Okay, so that's beyond red. What about beyond violet? Shorter wavelengths.
Right. Shorter wavelengths mean higher frequencies and generally higher energy. Just beyond violet, you find ultraviolet rays. UV light.
From the sun, the stuff that gives you a tan or a burn.
That's the one. Shorter still, you get X-rays.
Medical imaging, airport security.
Uh-huh. And finally, with the shortest wavelengths and highest frequencies, you have gamma rays.
Associated with radioactivity. And space.
Yes, very energetic stuff. So it's this whole continuum. Gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, radio waves, all electromagnetic radiation.
It's all fundamentally the same type of thing, just different sizes of waves.
That's a great way to think about it. It's all oscillating electric and magnetic fields traveling as waves. And crucially, in a vacuum, they all travel at the exact same speed.
The speed of light? C. $3 times 108 meters per second?
That's the one. And that equation, volley-dealy, applies across the entire spectrum. As wavelength goes up, frequency must come down, and vice versa, to keep the speed constant.
And the dividing lines between these types, like between UV and X-rays, they're not super sharp, are they? More like overlapping zones.
Exactly. It's a continuous spectrum. We just categorize ranges based on wavelength, source, or how we detect them.
Our sources had a great table summarizing them: discoverers, sources, detection methods, like gamma rays from radioactive nuclei, detected by photographic plates or Geiger counters.
Right. X-rays, famously discovered by Roentgen, produce when fast electrons hit metal, detected similarly.
Ultraviolet, from the sun or electric arcs, detected by fluorescence or chemical reactions.
Visible light, the sun is the main natural source, detected by our eyes, photographic film, photocells.
Infrared, discovered by Herschel from hot bodies, detected by heating effects using things like thermopiles.
Microwaves, from electronic devices, detected by specialized receivers.
And radio waves, from oscillating circuits in transmitters, detected by antennas and receivers.
It's a whole toolkit of radiation.
And despite all these differences in wavelength and how we use them, they share core properties, right?
Absolutely. Key things to remember. 1, they don't need a medium. They can travel through the vacuum of space.
Unlike sound.
Right. 2, they all travel at speed c in a vacuum. 3, they all exhibit reflection and refraction.
So they bounce off things and bend when they enter new materials?
Yes, though when they refract, their speed and wavelength change, but their frequency stays the same. Think of waves hitting a beach. They slow down and bunch up, but the number hitting per minute doesn't change.
Okay. Frequency is constant when changing media. Good point.
4, they aren't deflected by electric or magnetic fields because they're uncharged waves. And 5, they are all transverse waves.
Meaning the oscillations are perpendicular to the direction the wave is traveling, like shaking a rope up and down.
Exactly.
Let's zoom in a bit on infrared and ultraviolet, since they sit right next to the visible spectrum. Infrared, longer wavelength than red.
Yep, from about 800 nanometers up to a millimeter. We detect it mostly by its heating effect. A thermometer with a blackened bulb placed just beyond the red end of a spectrum will show a temperature rise.
Clever. And sources are basically hot things. Heated iron, flames, the sun.
Pretty much anything warm emits some infrared. Property-wise, it travels in straight lines, reflects, refracts, and because its wavelength is longer, it's scattered less by the atmosphere.
That's why it's used for night photography or seeing through mist.
Exactly. Less scattering means it can travel further through particles in the air. Also used in remote control, some therapeutic heating.
But too much can cause skin burns from it.
High-intensity infrared, yes, it's heat radiation after all.
Okay, now ultraviolet. Shorter wavelength than violet.
Down from about 400 nanometers to 10 nanometers. Detected by chemical activity, it can affect photographic plates, cause fluorescence.
Fluorescence, like those posters that glow under black light.
That's UV at work. Sources include electric arcs, sparks, special mercury vapor lamps, and of course the sun. Though, thankfully, the ozone layer blocks a lot of the most harmful solar UV.
And it doesn't pass through normal glass.
Mostly absorbed by ordinary glass, yes. But it passes through quartz. That's why you need quartz prisms and lenses if you want to study or work with UV light specifically.
Properties. Travels in straight lines, reflects, refracts, causes fluorescence, and has a strong effect on photographic plates. Uses.
It has sterilizing properties, killing germs, used for detecting purity like checking gems or eggs, and it plays a role in our bodies producing vitamin D.
But the downside is risk of skin cancer with too much exposure.
Unfortunately, yes. That higher energy per photon can damage DNA.
It's amazing how each part of the spectrum has such distinct interactions and uses, even X-rays revealing crystal structures.
Or gamma rays used in cancer therapy because of their penetrating power. It's all connected, but wonderfully diverse.
Okay, there's one more really cool light phenomenon we need to talk about. Scattering. This seems key to understanding why the sky is blue, sunsets are red, all that stuff.
Yes, scattering. Crucial stuff.
So what is scattering exactly?
In simple terms, it's when light interacts with particles, could be air molecules, dust, water droplets, and gets absorbed and then re-emitted, usually in different directions. Bounced around, essentially.
Okay, it hits something and goes off in a new direction.
Right, and how it scatters depends hugely on the size of the particle compared to the wavelength of the light.
Size matters here.
Definitely. For particles much smaller than the wavelength of light, like nitrogen and oxygen molecules in the air, we get what's called Rayleigh scattering.
Rayleigh scattering, got it. And what's special about that?
What's special is its incredibly strong dependence on wavelength. The intensity of the scattered light is inversely proportional to the fourth power of the wavelength.
Whoa, the fourth power. Lambda to the power of 4. $1 lambda 4.
That's the one. It means shorter wavelengths get scattered way more strongly than longer wavelengths.
So violet and blue light, with their short wavelengths,
get scattered much, much more intensely by air molecules than red light with its longer wavelength.
How much more?
Well, violet light's wavelength is roughly half that of red light. 2 to the fourth power is 16. So violet light is scattered about 16 times more effectively than red light by the air.
16 times. Okay, that's significant. And what about bigger particles, like dust or water droplets in clouds?
When the particles are larger, comparable to or bigger than the wavelength of light, the scattering becomes less wavelength dependent. Larger particles tend to scatter all colors more or less equally. That's sometimes called scattering.
Okay, small particles, air, scatter blue-violet most. Really. Large particles, clouds, scatter all colors equally. Mi'ikana. This explains so much.
It really does. Think about the color of the sun at sunrise or sunset.
Right. The light has to travel through way more atmosphere to reach you than compared to noon.
Exactly. A much longer path through those air molecules. So what happens to the blue and violet light?
It gets scattered away 16 times more effectively. By the time the light reaches your eyes, most of the blue and violet has been redirected sideways.
Leaving
the longer wavelengths, the reds and oranges, which are scattered much less. So the sun looks red.
Bingo. And at noon?
Sun's overhead, shortest path through the atmosphere. Less scattering overall. And maybe the scattering of different colors is more balanced or just less pronounced. So the sun looks whitish or yellowish.
Pretty much, yeah. Less preferential scattering over that shorter distance.
Okay. Mind blown about sunsets. Now, the blue sky. Why is the sky blue when you're not looking at the sun?
Same principle. The sunlight streaming through the atmosphere gets scattered by the air molecules. Which color gets scattered most effectively in all directions?
Blue and violet. Because of Rayleigh scattering.
Right. So when you look up at the sky away from the direct sun, your eyes are receiving all this blue light that's been scattered sideways from the original sunbeams. Our eyes happen to be a bit more sensitive to blue than violet, and the sun emits slightly less violet, so the net effect we perceive is a blue sky.
Amazing. And if there were no atmosphere, like on the moon?
No air molecules, no scattering. The sky would look completely black, even with the sun shining, because no light would be scattered towards your eyes from other directions. You just see the stars.
Just like the astronauts saw. Okay, what about clouds being white?
Clouds are made of water droplets or ice crystals, which are much larger than the wavelengths of visible light.
Right, so they're the large particles.
Which means they scatter all wavelengths, all colors of sunlight, more or less equally. Me scattering.
So white light goes in, gets scattered in all directions, but it's still white light coming out, hence white clouds.
Exactly. Unless they're very thick and block the light, then they look gray or dark.
Makes sense. And finally, danger signals being red. Why red?
Longest wavelength in the visible spectrum.
Least scattered.
Least scattered by air molecules, fog, mist, haze. So the red light can travel the farthest through the atmosphere without being weakened or dispersed too much.
Making it more visible from a distance, especially in bad weather. It cuts through the crud better.
That's the idea. It maintains its intensity over longer distances.
Wow. Scattering. It connects so many everyday things. The color of the sky, sunsets, clouds, warning lights. All down to how light interacts with tiny particles and its own wavelength.
It's a beautiful demonstration of physics in action all around us.
So let's try and wrap this up. We started with a simple prism.
And saw how it splits white light, revealing it's actually a mix of colors.
Because different wavelengths, different colors, bend by different amounts as their speed changes inside the prism material. That's dispersion.
Then we zoomed out, realizing that the visible rainbow is just this tiny sliver of a huge electromagnetic spectrum.
Gamma rays, X-rays, UV, visible, infrared, microwaves, radio waves, all the same fundamental wave, just different wavelengths traveling at the speed of light in a vacuum.
All with unique properties, sources, detection methods, and uses from medical imaging to communication.
And finally, the phenomenon of scattering, especially Rayleigh scattering, explaining why the sky is blue, sunsets are red, and why red is used for danger signals. All based on how light interacts with particles, particularly that strong dependence on wavelength.
It's quite a journey, from a simple glass triangle to the color of the sky.
It really is. And thinking beyond this, what's a final thought for people to chew on?
Well, maybe think about how this interplay of light, wavelength, and matter creates color in other ways. Not just prisms and scattering, but say the iridescent colors on a butterfly's wing or a soap bubble.
That shimmering effect. That's not pigment, is it?
Often it's not pigment, but structure. Tiny, intricate structures on the surface that cause light waves to interfere with each other, canceling some colors and reinforcing others, depending on the viewing angle. It's called structural coloration.
So understanding waves and wavelengths unlocks even more ways nature creates color. Fascinating.
Or even the technology in your phone screen, how it precisely controls red, green, and blue light to create millions of different colors through additive mixing. It all comes back to manipulating light.
It really makes you wonder. What other everyday things are hiding these incredible layers of physics and complexity, just waiting for us to look a little closer and ask, how does that actually work?
Yeah.
Thanks for diving deep with us today.